Hello, my name is Matthew Graham at the Center for Data-Driven Discovery at Caltech, and this module is about a broad overview to algorithmic approaches to working with big data. You'll have heard in Julian Bunn's talk about hardware that we can use, services that we can use to deploy algorithms and computing in for working with complex and massive data sets in the cloud, on grid, and that sort of thing. In this talk, I'm going to talk about some of the broad algorithmic decisions and ideas that you may want to think about when using those types of resources. So the main one, or the main idea behind many of these is a sort of divide and conquer type approach. Many computations in sciences which are working with very large data sets, and we'll take astronomy as our example one, are either what's known as pleasantly parallelizable or embarrassingly parallelizable. The idea here is that what you want to do to one single pixel or light curve or data item, you want to do to many, and so therefore you can divide the task that you want to do over as many computational resources as you have available to you. And this is realizable as the sort of intersection of the computing resources plus the code plus the algorithm. But the basic idea is that you have your task y, which is the sum of the same function that you want to do over many, and this is commonly referred to as the sort of map-reduce type problem. We'll consider that a bit more in a minute. So one of your basic problems when you're actually working with these type of algorithms is how to access the data itself. Where is the data? You will have hopefully watched the modules on relational databases, and they are very good for handling large amounts of data, make data access very easy. But there is this sort of maxim that when your data set is bigger than about 300 terabytes in size, working with it in a relational database becomes difficult. And you may then be working with it in some sort of non-relational database or a NoSQL, and you can watch one of the modules in the database section on some discussion of that. There's always an assumption that the networking is sufficient to cope with the sort of data access that you want to do. But what happens if you're not working with a database and you just have your files in some sort of distributed file system? Well, there are a number of technology solutions that you may want to consider. Distributed file systems like Lustre, or such as HDFS, which is inspired by the Google file system for distributed data. Alternatively, you may want to not work with flat file systems, but work with something where your data is actually in some sort of structured store. As we've said, relational databases probably not good if you're working with sort of petascale stuff. Though there are some solutions to that. QServe is a piece of software which sits over MySQL instances and federates those and uses XRootD, which comes from the particle physics world, to do some of the resource management. And this is the system that's going to be used by the LSST project to manage their petabytes of data. So it essentially gives you a very relational database-like environment to pull your database out of, to pull your data out of. SciDB is another piece of technology that's aimed very much at scientific data. It's a column-oriented database as opposed to row-oriented, and it tends to work with arrays as the first-level data objects rather than tables. It also maintains ACID, which is good, as you'll remember from the database modules. So that's another thing to have a look at that has come out of the BABA project at Stanford. As I said, there may be no SQL options that you want to look at. These are very largely optimized key value stores, so they're good for working with web scale transitions, but not necessarily with complex data objects. And then there is the so-called new SQL data store type things like HStore, which is we'll probably mention a bit more in a minute, and Google Spanner. These are relational models underneath. They support SQL, but they're sort of a crossover between the relational databases and the highly optimized key-value stores that you get with no SQL, and trying to take the best of both worlds and use sharding middle layers and things like that to optimize where the data is and data retrieval. So if you're working with large amounts of data, those are the sorts of data stores you may be looking at. In terms of the hardware that you may want to use to run your algorithms on, these types of problems are very different from just solving partial differential equations, which means that you're not looking for a big supercomputer in the basement it's got large amounts of shared memory and MPI. You're just looking for something where you can throw a whole load of cores or CPUs at the sort of problems. Julian Bunn has already talked about the cloud and on-demand computing, where you can deploy what you want when you need it, get access to the amount you want to. That this may not necessarily be cost effective, particularly for data transfer. Another option you may want to consider is that the size of your computation is larger than what you may have available on your desktop, but within the realms of what you can do with a graphical processing unit, a GPU. Every computer these days has at least one GPU in it, normally on the graphics card running your gaming graphics, but you can easily use them for your own computations. And you'll find that the high-end GPU cards have up to 2,500, 3,000 cores per multiprocessor. Each core can run sort of 16 threads, so that gives you about 40,000 threads per GPU. These are very lightweight threads, very different from the sorts of things you may have encountered if you're doing traditional threaded programming. And it's very easy to launch up to 1 billion threads per second. What this means, though, is that there's a different style of coding and algorithms designed that you need to use if you're actually working with GPUs. And so actually they favor far more the brute force approach than maybe some intelligence or subtlety in your algorithms. So it's actually much easier to write a GPU code which is very basic but will run faster than a smarter algorithm designed to do the same thing that's running on the CPU, just because you can throw so many more cores at it. An example is, for example, n-body correlations or endpoint correlations. One issue with GPU, however, is that there are memory issues because they use a different memory cache from the normal CPU memory cache, and so the amount of memory that they have available for computation is not very large, so that limits maybe the size of the computation you can necessarily do in a single thread. There's also a latency issue from data that needs to be transferred from the CPU memory to the GPU memory. So these are things you need to be slightly wary of or considerate of when you're programming for the GPU. So let's go back to this way of working with embarrassingly parallelizable jobs. This is the MapReduce paradigm. It came out of Google. It's really still the primary choice for fault-tolerant, massively parallel data crunching. And if you have to do large-scale processing or working analysis of any data, it's really the sort of sledgehammer that you want to use to crack your nuts. It's based on functional programming, map and reduce functions. As we said in the introductory slide, you consider it to be a decomposition of your work into a summation, which is the map, and the function, which is the reduce. Sorry, other way around. And it allows reliable processing, even though machines can die, because you're running this on a very large cluster. So if one of them drops, it doesn't matter, and one of the other ones will pick it up. And it allows very large parallelization. The records for sorting terabyte and petabyte data sets all rely on MapReduce in some form. The old record was 1 petabyte of data could be sorted in 6.8 hours using about 1,000 cores, I think it was, and that record has now been reduced to just under 4 hours using the Spark infrastructure, which I'll mention in a few slides, and again, several thousand cores. But it's using a sorting algorithm which has been very highly parallelized, but it's making use of this MapReduce paradigm. MapReduce is used in astronomy, as an example, in a number of areas. It's been used in image coedition pipelines, where 100,000 Sloan images from the Sloan survey were co-added, and the idea was to do a comparison of different ways of doing this. The MapReduce algorithm using Hadoop, which is a implementation of MapReduce from Apache, allows you to do. Using that infrastructure, they were able to do this task which would not have been traditionally computationally possible. And the idea is to use the most successful pipeline that they've produced, scale it up to handle petascale data that'll come from LSST. The Berkeley Transient Classification Pipeline makes probabilistic statements about transients. It's a time domain survey. But again, it used Hadoop to identify different algorithms that would be very appropriate for working with different sky conditions and possible different cadences and things like that. It used a particular part of a Hadoop called Hadoop streaming, which allows you to work with a streaming data, with a data stream, rather than with a static data. Makes use of a thing called cascading package, which is for wiring things together. And the intent is certainly in the publications to use what's called Mahout and Hive, which are different libraries under Hadoop. And finally, there's another example, is the large survey database. This is again, it's intended to be a data store, at least a terascale, but if not a petascale terastore, a data store for astronomical data. It's used by the Pan-STARRS 1 for data analysis, and it's also used by the Palomar Transient Factory, and it has an in-house MapReduce system within it. This is open source software, so you can go to GitHub to find this piece of software to use if you want. But instead of relying on Apache Hadoop, it uses a self-constructed MapReduce system, but it's still employing this idea of breaking up these very large jobs into very small components and splitting them over many CPUs and cores. So I've been mentioning Hadoop a bit. What is it? Hadoop is a suite of packages that come from Apache, open source software. So it offers you a variety of different functionality. It gives you a distributed file system. It gives you can give you a column-based database. It can give you a pseudo-relational database with a variant of SQL that can be used with it. It has a scripting language attached to it that you can employ. It has various things for coordinating services and running cloud services, connecting different components together to make workflows. If you have your data available, you can, in a relational database, you can put Scoop on it, for example, to make it then accessible into the rest of the Hadoop system. And then there is also a machine learning data mining library available called Mahout, which has a variety of algorithms which have been implemented in such a fashion to make use of the underlying Hadoop system. So all of these make use of MapReduce, but they're making use of MapReduce to carry out the various functionalities that they provide in a cloud environment. So if you have need of a particular piece of infrastructure, there's probably a piece of software within the Hadoop suite that will allow you to do what you want to do. One thing that needs to be said about MapReduce is that there are possible problems for it when you're working with very large machine learning algorithms, or when you're working with machine learning algorithms with very large data sets. This table here gives some indication of one of the problems that you may have. Some of the algorithms only require a single iteration, and that's perfectly fine for MapReduce. But when you start having algorithms where you need to have multiple iterations through the data, or where you need to persist information between iterations, or there is some notion of shared memory, shared information between iterations, then this becomes difficult for MapReduce. This is particularly the case for things like support vector machines or hidden Markov models, though there are now variants of the MapReduce algorithm which are designed more to support these type of operations. Things like iterative MapReduce, for example, can be used in these sort of environments. So if what you're wanting to do is to run a very large machine learning algorithm on a very large data set, and you're looking at MapReduce as the way to do that, you may want to consider whether it is the appropriate way of doing it or whether you can actually do it. But there may be more experimental ways of using MapReduce to do that. Alternates to MapReduce, the so-called no Hadoop school, which sort of came around a few years ago because people were a little tired of MapReduce being said to be the solution for all big data problems. There's a project called Percolator, which came out of Google, and the idea is that it allows you to incrementally update massive data sets continuously and working in that sort of streaming fashion, and it provides an infrastructure for working with that sort of data set, more so than sort of just a very static one. So it's aimed very much at the sort of web scale things where you've got constant feeds of Twitter tweets or Facebook updates or whatever coming in. There's a thing called Apache Hama, which is an implementation of the bulk synchronous parallel algorithm. This is a way of doing MPI type calculations, but where you can split it across very many machines, very many clusters, and it avoids some of the problems of MPI in those situations. There's a thing called Pragle, which is an infrastructure for working with very large graphs. So again, if you want to do sort of web scale analysis, where you have very large linked data sets with billions of nodes, trillions of edges, Pragle is the sort of thing you might want to consider. Makes use of this BSP algorithm underneath. And what you can consider where it may be appropriate is if you had very large for example, very large astronomical catalogs, which you want to do cross-matching, positional matching from one catalog to the other against in bulk. So you may have two very large graphs which you then want to compare against each other, and that may be one possible way to do that. Another way that has come up more recently is the second generation or the next generation of Hadoop, which is called Yarn. This came out of a realization that the Hadoop infrastructure was maybe a little limited in what it was offering to work with complex and massive data sets, because it was only allowing you to do the MapReduce algorithm, and maybe there are other approaches or interaction patterns for data which allow you to do your calculation more efficiently. And it's based on top of HDFS as the distributed file system underneath, and then you have Yarn, which sits as a layer on top. Again, it comes out of Apache, and then you can have MapReduce sitting on top of that, or you can have other interaction patterns for your data instead. And so it vastly increases the amount of ways you can actually encode and work with your data. And it offers, there are a number of new services, new frameworks which are based on top of that. There's Hoya, which is an H-base, so that's the relational database again, which can sit on top of Yarn. There's a framework for working with directed acyclic graphs. There's Spark, which is an infrastructure which has machine learning library in it. Or if you want to do graph processing, then there's a thing called Giraffe. These are all Apache projects, so you can go to the Apache pages and read the descriptions about them and how to work with them. But these give you possibly different infrastructures for working with very large data through the Hadoop system and employing all the benefits of that. Now, you come to the final question of, well, do you actually really need any of this? Maybe I can just be smart about how I'm writing my algorithms. So I'm just going to talk about 2 or 3 different ways that you can maybe think about parallelizing algorithms, which maybe mean you don't need to go and use MapReduce and try and rewrite your computation in terms of MapReduce. So we'll take as our canonical analysis algorithm that I want to do k-means clustering, particularly as this is one of the ones that is identified as maybe making a little difficult for a standard traditional MapReduce because of the number of iterations and because there is also some persistence of information between iterations. K-means has been covered in one of our machine learning modules. So briefly, you just start with k cluster centers, where k is a number that you can choose randomly, or you have some recipe for guessing the number of clusters that there will be in your data set. You assign each data pointer to its nearest cluster center, where the distance metric is defined in some way. You then reevaluate the cluster centers as the average of the data that you have, and you keep repeating this, assigning each data point to its nearest cluster, reevaluating the cluster centers until the cluster centers don't change or some stopping criterion has been met, that you have reduced or maximized some loss function or weight function, something like that. So you can run that serially in that fashion, and it will take an amount of time. So the first question is can I convert this into something that's parallelized, so that maybe I don't need to wait a long time on a single core. I can throw it against the 100 or 1,000 cores I may have available to me on a cluster in my basement and reduce my computation time for doing my clustering by that amount. If you have large amounts of data that don't need to be sent around to processors, this works. You can also think about k-means that if you're doing the same thing on each processor, there's minimum interprocessor communication, and the data set needs to be read by each iteration, but each point actually would only need to be read by one processor. So if you've got 1,000 processors working on this, you can divide the data up into 1,000 subsamples, and though you're going to read that whole data set for each iteration that those 1,000 cores are going to carry out, you will actually only need each data point to be read by one processor, not across. So in terms of parallelization, essentially which is MapReduce in this case, you divide the data amongst the processors. Each processor will read the previous iteration's cluster centers, so that's the piece of information that needs to be persisted, and assigns the data, the subsample of data that it's working with to those clusters, and then each processor will then calculate the new centers for its data, and then you aggregate the results of each of those 1,000 processors, doing a weighted average to give you the true cluster centers, which is the information you persist over to the next iteration. And you would then reiterate again with those as the new cluster centers that you would run through. So this is optimized for large data. It makes use of local clustering, and you're only working with average quantities to persist from state to state, which are techniques that you can think about whether your algorithm can be broken down into that fashion, and so making itself suitable for k-means, making it suitable for parallelization. Now, what happens if I don't have persistent data? What happens if I have a data stream? So the case here is that I want to do k-means clustering on my data, but my data are too large to store on available resources. I know I'm going to be working with a petabyte data stream, and I only have, 100 terabyte of data storage available, or maybe there's too much data to hold in memory. Maybe the data are not persistent, so later processing is not possible. This is true of some very large science experiments where they don't keep the raw data, but you may want to work on the raw data as it's streaming through because you wouldn't be able to do that. This also allows for rough and ready results required for data exploration, for example, and maybe you're after checking convergence or data quality in an ongoing fashion with your underlying data stream. So a way to have an online or a streaming algorithm of k-means is that in this case you would make initial guesses for your cluster centers, and then you set a number of accounts for each cluster center to 0, and you start looping in the following way. You get the next piece of data, you find the center that's closest to it, you increment the count of the cluster, and then you replace the cluster center by a weighted term and an incremental term, or a weighted incremental term, which is given by the expression there. And this will converge and give you the same answer as if you were running on either the parallelized form or the serialized form of the k-means. But this way of doing it allows you to run on a data stream as opposed to a data file. Finally, there is another way of working with these sort of large algorithms that you may want to think about, and this is the so-called stochastic algorithm approach. One of the problems with k-means is that it's very prone to local minima, and it can be quite sensitive to where you establish those initial cluster centers. So normally you may have to repeat your k-means algorithm several times just to make sure that you are converging on proper cluster centers, particularly if you're working in a very high-dimensional space. A stochastic algorithm is said to be able to reach a global minimum quicker, and nominally it can work with a subset of the data. It doesn't necessarily have to work with a full data set. At least the relative positions of the clusters in the stochastic k-means can be found very quickly. Final convergence can be slowed down, but with the right learning algorithm, you can converge quickly enough to what you believe is the true answer. And the way you make use of this is that you have to make an assumption about what the learning rate is for the algorithm, and you have a loss function. So if we used the loss function that we gave with k-means in the first slide, it turns out that the learning rate gives us exactly the same version as in the online version of the algorithm. So that update term in the online version, in the streaming version of the k-means, is exactly the same as the term that you use in the stochastic k-means algorithm. So in that case, this means the stochastic and the online version are equivalent. So if you're working with large data sets and you're wanting to do a sort of computation with them, it may be worth thinking about are there different ways that I can implement my algorithm in terms of not just a serial form, but a parallelized form, or maybe an online form, or maybe a stochastic form, which will allow me to get to an answer quicker than just if I was doing it in a particular case, and can I deploy that on different computing resources? So these are the things to think about and to follow up further in more advanced material when you're thinking about the sorts of algorithms that you want to use when you're computing with big data. Thank you.